and those points at which function is not analytic were known as singular point. So that singular point was classified in mainly three parts: poles, essential singularity, and removal singularity. And either pole or essential singularity or removal singularity can be isolated or non-isolated singularity. So I think the definition of isolated and non-isolated singularity were also clear. Now the today topic is residues at a pole. So let us define the function fj. Let us assume that the function fz has a pole of order m. I hope with this sentence everything is clear in your mind. Fz has a pole of order m at a point z equal z naught means the principal part of Lorentz series having finite number of terms, that the maximum power of the denominator, maximum power of z minus z naught in the denominator is m. So fz has a pole of order m at z equals z naught. It means fz is not analytic at z equals z naught. Now, so let's even with the circle of radius r with center at z equals z naught, which does not contain any other singularities except z equal to z naught. Why we are doing these things? Because yesterday we have been discussed already. Then the function fj is analytic within an endless region this. Within an endless region. So therefore, by Lorentz series, we get this expression. I'm always talking about 2 points, two theorems: Taylor series and Lorentz series. Taylor series and Lorentz series. Taylor's and Lorentz. Just I'm drawing the picture here, although already I've been discussed this one. It means if a function fz is analytic within and on a circle this C centered at z naught and radius r, then fz will be expressed like this one, only half of the part, this one, and this is known as the Taylor series expansion. Again I'm repeating, if a function fz is analytic within and on this circle C centered at z naught and radius r, then the fz for all value of z inside this C can be expressed as fz summation an z minus z naught to the power n, where n varies from 0 to infinity. For n, this an can be evaluated with the help of this formula, that n is 1 upon 2 pi I fj divided z minus z naught to the power n plus 1 dz. C2 means, in this case, C2 will be C simply. Please try to understand the things. Again and again I am repeating. If a function fz is analytic within and on this circle C, centered at z naught and radius r, then function fz for all value of z inside this C can be expressed in terms of series like this one. This way, where an is what? N is 1 upon 2 pi I integration fz divided by z minus z naught to the power n plus 1 dz. And this series is known as Taylor series. But if a function fz is analytic, fz is analytic This one, where it is analytic, like this one. Here, this is one circle, this is another circle. So, what is going to happen? The function is analytic. Function is analytic within a region, in an endless region. Function fz is analytic in an endless region bounded by two concentric circles C1 and C2. Bounded by two concentric circles C1 and C2. Then fz for all values of z within the endless region can be expressed like this one. A series form. Fz equal to summation En z minus z naught to the power n and summation Vn z minus z naught to the power minus n. Be careful. In this case, n varies from 0 to infinite, but in this case, n varies from 1 to infinite. And in this case, what are the An and Bn? An is this one and Bn is this one. It is important point that C2 and C1. What is C2 and C1? So you may see C1 is the inside circle. C1 be a circle where its center Z0, which does not contain any other singularity except Z equals Z0. Then the function fz is analytic within the endless region. It means mod of z minus z0 greater than r and less than r. What is r? R is the circle, r is the radius of the outer circle. C2 equal to mod of z minus z0 equal to r. So C2 is the outer circle. So the value of an can be evaluated with the help of this over this outer circle C2 and Bn over the inner circle C. So this is Taylor series. Again I'm repeating. Be careful. In the Lorentz, in the Taylor series, our function was analytic entire this region. Center at Z0 and radius r. Then fz was expressed like this one only because there were no singularities. But in case of Lorentz series, function is analytic in an endless region bounded by two concentric circles C1 and C2 centered at Z0. Then fz for all value of z which lie in an endless region, fz can be expressed like this one, where an is this and bn is this, and this is known as the Taylor series expansion. Already I have been discussed yesterday, but I try to discuss in details today. So I hope the point is clear about the Taylor series. We are not going to prove this one here, but you may remember this one, that this is the exponential. Now, why I discuss it? Because it may help us to find the residue at a point. Anyway, so this is Taylor series. So what was happening in this case? That fz has a pole of order m at z equals z0. So fz has a pole of order m at z equals z0. It is z0, this creating problem because function not analytic at z0. That's why what we did, we construct a circle centered at z0 and radius r, as shown in picture. This one, small circle, small radius r. So we are going to construct circle in such a way that this circle does not contain any other singularities except z equals z0. Then the function of z is analytic within an endless region. Endless region is this one. In this one, endless region bounded by this one, Therefore, by Lorentz series, you will get like this one and n bn. Now, particularly when n is 1, then b1 will come 1 upon 2 pi I integration over c1 fz dz, where mod of z and z not equal to 1. So this coefficient b1 is called the residue of fz at the pole z equal to 1. This is the principal part. So here the value of b1 is the coefficient of 1 upon z minus z naught. What is b1? You may see here in the expansion part, b1 is the coefficient of 1 upon z minus z naught. Then that b1 is the coefficient of z minus z naught is known as the residue of the analytic function at pole z equal to z naught. And the value of b1 from this formula is nothing, it is integration fz dz over c1. Symbolically, we may write this one, the residue of fz. You may see the screen here. Residue of fz at z equal to z naught is b1. Is there any doubt, please? Anyone want to ask a question? Then you may ask a question, please. You may raise your hand. No one. Shivangi?
So actually she has some mic issues, that's why she is not able to speak today.
Okay. So, is it clear the definition of residues?
Yes, sir.
Now, residue at infinity. Now we will study residue at different points. Here it is residue at a pole. But we will discuss this one separately, that residue at a simple pole, residue at a pole of order m, residue at another function. So slowly we will move. Now next point is residue at infinity. The residue of function fz at z equal to infinity is defined as, so there 1 upon 2 pi I integration fz dz, but here with the negative sign, minus 1 upon 2 pi I integration fz dz. But the integration is taken around C in anti-clockwise direction, and C is a large circle containing all finite singularities of that. So if someone will ask to find the singularity at infinity, then we may use this formula and we can get that. Now there's a few methods to find the residues. So first is residue at simple pole. Residue at simple pole. So if a function fz has a simple pole at z equal to z naught, then residues of fz at z equal to z naught will be nothing. It is limit z minus z naught into fz z tends to z. I hope you all may agree with this one. You may prove this one immediately. Just a minute, may I see whether the proof is given here? Yes, proof is given here. So we may prove this one simply. I am showing the proof of this. Next slides. So you may see, since function fz has a simple pole at z equal to z naught, means fz can be expressed like this one. Simple pole means there is only one term in the principal part of the Lorentz series. So this part will be there, but only one term will be in the principal part of the Lorentz series. Now already we have seen that this b1 is the residue of the function fz z equal to z naught. So means we need to have this b1. For this b1, just multiply this whole both sides by z minus z naught. So this is going to be z minus z naught, and here again z minus z naught to power n plus 1 plus 3. So now b1 means just take the limit on both sides at z tends to z naught. So here limit z tends to z naught, z minus z naught fz. When we take the limit at this position, here we can't take that because fz is unknown. So it will be in the limit form. But here an is constant. It is not function of z. So we may take the limit at z tends to z naught, and at z tends to z naught means n is 0, then z minus z naught. N is 1, then z minus z naught square. N is 2, then z minus z power 3. It means every terms will contain z minus z naught. So when we take the limit at z tends to z naught, so all terms will vanish. So here we will get b1. So b1 is ultimately coming limit z tends to z naught, z minus z naught fz. And by default, this b1 is the residue. That's why residue of a function fz at z equals z naught is nothing. It is limit z tends to z naught, z minus z naught into fz. I hope it is okay. Now next is another way. If a function fz is of the form of fz equal to phi z divided by psi z, where psi z not equal to 0. What this shows? Psi z not equal to 0 means this fz is not analytic at z equal to z naught. Psi z naught is 0, but phi z naught not equal to 0. So that will indicate that this function fz is not analytic at z equal to z naught. We are not sure about this point, whether it is pole or similar, whatever there, but it is not analytic at z equal to z naught. So in this case, residue of the function fz, when function fz will be in this form, can be evaluated like phi z naught divided by psi dash z naught. Okay. So now we may prove this again. We already know that the residue of fz at z equal to z naught is limit z tends to z naught, z minus z naught fz. Just we prove it earlier in the previous section. So the value of fz is phi z by psi z we have been used. Now take the limit at z tends to z naught. You know what will happen? Z tends to z naught, it means psi z naught is already 0, and z tends to z naught means it is 0. It means it will come in the form of 0 by 0, which is not defined. So we need to evaluate this limit. What we are going to do, we are going to express this function. Express this function about z naught as a Taylor series expansion. So phi z will be phi z naught plus z minus z naught phi dash z naught plus 1. You all know the expansion of this one. Similarly, we may express psi z like this one. The same concept. Now again, take the limit at z tends to z. So this value psi z naught is already 0. So from the denominator we may take common z minus z naught. So from that z minus z naught, this z minus z naught will cancel out. So here first term will be psi dash z naught. Second term will be z minus z naught by factorial 2 psi double dash z naught plus 1. And in numerator first term will be this one. So when we take the limit, then in numerator all terms will vanish except first term, and also in denominator all terms will vanish except first term. So ultimately what you get? Phi z naught divided by psi dash z naught. So this is another way to find the residue of the function fz. So we have been learned two ways to find the residue of the function fz. If z equal to z naught be a pole of order, simple pole of order m, then limit z minus z naught fz, and if fz is in the form of phi z divided by psi z, and psi z naught is 0 but phi z naught not equal to 0, then residue will be phi z naught divided by psi dash z naught. Now third one, residue at the pole of order n. residue at a pole of order n. So we have been seeing the residue at a pole of order 1, but here we need to find of order n. Of order n is the principal part contains n finite terms. So what the form of order that one? If a function fz has a pole of order n at z equals z0, then residue of fz at z equals z0 will be 1 upon factorial n minus 1. And once one of the derivative of this expansion, it means z minus z0 to the power n fz at z tends to z. Okay, so now let's see the proof of this one. Since the function fz has a pole of order n, already I told you, then the principal part of Rn series will contain n finite terms. It means fz can be expressed like this one. This term will be as it is, but the in principal part will be like this one: b1 by z minus z0 plus b2 by z minus z0 square plus so on. Now, we all know that ultimately b1 is the residue. So our aim is to find the value of b1 from this expression. So what we can do, we can multiply b1, but if b1 if we are going to multiply whole expression by z minus z0, then b1 will be here, but here will in denominator z minus z0, here z minus z0 is square. So in denominators we are getting z minus z0, that will make the limit as infinite. So to find the limits, what we can do, we can multiply whole things with z minus z0 to the power n, so that the term from the denominator, term of z minus z0 from the denominator will be removed. So z minus z0 to the power n, and it will give us the every places n. It means here n is 0, then n plus 1, then n plus 2, and then so on. It is from this term. Then for here we are multiplying by z minus z0 power n, so it means b1 z minus z0 to the power n minus 1 plus n minus 2, and then so on. Already I told you that our aim is to find the value of b1. So you may think how we can find it. If we take the limit at z tends to z0, then again it will be a problem, it will become 0. So our problem is not solved. So to find the value of b1, what we can do, we can differentiate this equation both sides. How many times? N minus 1 times. Why? When maximum power is n minus 1. You all know that if x square is there, x square means for 2, then maximum derivative we can find up to second order. It means first 2s, then second 2, and third it will be 0. So if x to the power m, then maximum derivative will be up to nth order derivative. But and other m plus 1, m plus 2, m plus 3 all will give us 0. So because of this one, we can differentiate this whole with respect to z up to n minus 1 times. So first we will differentiate, then n minus 1 will come. Second, then n minus 2 will come. So n minus 1, n minus 2, n minus 3, and so on. 3, 2, 1. And these are the less than n minus 1. So as I told you that when we will differentiate x square 3 times, then the result will come 0. X square 4 times, then the result will come 0. So same concept is there. It is n minus 1 is there, n minus 2 is there. So when we are going to differentiate is n minus 1 times, n minus 1 is greater than n minus 2. So this term will be 0. This term will be 0. The separate term will be 0. In this case, this will be 0. But here, n minus 1, n minus 2, n minus 3, so on. It means factorial n minus 1. So b1 into factorial n minus 1. And left side, we are differentiating n minus 1 times, so n minus 1 the derivative of this one. We will differentiate it. And then we need to take the limit as z tends to z0, because all these, the derivative of all will give 0, but the derivative of all these will not give the term 0. It means n1 derivatives will contain z1 z0. So to find b1, we need to take the limit also. So differences both are equal to n1 times, and taking limit as z tends to z0. Z tends to z0. Then when we will do this procedure, then we'll get like this one. So thus b1 is 1 upon factor n minus 1, and minus 1 of the derivative of this expansion z minus z power n fz at z equal to z. And b1 is nothing, it is residue of fz. So residue of fz at 0 z0 is this. So if fz has a pole of order 1, then residue of fz at 0 z0 will be z minus limit z minus z0 fz at z tends to z0. But if it has a pole of order n, then residue will be 1 upon factor n minus 1, and minus 1 of the derivative of z minus z0 to the power n. Now next is the residue at a pole z equal to z0 of any order, that is simple R of order n. So already I have been told that nothing to the coefficient of z minus z0. Because residue from the beginning, when we start the residue, so residue was b1 was the coefficient of 1 upon z minus z0. So you may go with these methods, or if you expand the function, then whatever the coefficient of 1 upon z minus z0 will come, that will be the residue of the function fz at z equal to z0. Okay, so the proof is again very simple. If the function fz has a pole of order n at z equal to z0, then by balance with this one. And we know already that b1 is the residue of fz at z equal to z0. So just we assume z equal z minus z0 equal to t. So z will come z0 plus t, and fz0 plus t will come like this one. Then therefore the residue of fz is the p1 is the function of 1 upon t. Is z equal to z0 in the function fz. So this is the important note. If we anyone asked to find the residue at z equal to 2, 3, so just use z equal to 2 plus t in the expansion of that one, and expand that, and then coefficient of 1 upon t will give us the residue of the function at z equal to 0. Already we have discussed the residue of fz at z equal to infinite. This is another way to find that residue of fz at z tends to infinite can also be evaluated as limit z tends to infinite z minus z into fz. Now, so it means we have been studying the concept of the residue, so that will play more. We will solve some problem based on it. Now, first question, find the residual function z cos 1 by z at z equal to 0. So before going to find the residue of the function, we must ensure that what is z equal to 0. Z equal to 0 is a pole, or what is that? So in this case, we may expand this z cos 1 upon z. Cos z means z is okay, 1 minus 1 upon z square factorial 2, like this one. So we will multiply both sides in this one by z. So first term will be z, second term will be 1 upon z, plus 1 upon 2 1 upon z plus so. So as per the definition, residue at z0 is the coefficient of b1 B1 is the quotient of 1 upon Z. So 1 upon Z is here and its coefficient is 1 upon factor 2 with minus sign. So minus 1 by 2 is the coefficient. So it will be the residue of Z cos 1 by Z at Z equal to. Next question. Find the poles and residues of the function Z equal to Z upon Z minus 1 at the pole. It's a very simple question. You may find that this function is analytic everywhere except Z equal to 1. So Z equal to 1 is a singular point, and in fact that point is a pole of order 1. So in order to find the residue at the pole of order 1, simply multiply this expression with Z minus Z naught, sorry, Z minus Z naught, that is Z minus 1, and take the limit at Z tends to 1. So Z minus Z1 to Z minus 1 will cancel out, Z will there, and limit Z tends to 1 means 1. So residue of the function will be 1. Yes, please. Now who will solve this question? Already I will solve. Find the pole and residue of the function this one. So again, by equating denominator, we may find the points where the function is not at. So Z equal to 1, 2 and 3. But Z equal to 1, so this is a pole of order 4. Z equal to 2, it means it is a pole of order 1, and it is a pole of order 3. So residue at Z equal to 2, it means nothing, just multiply this whole with Z minus 2 and take the limit at Z tends to 2. Residue is coming minus 8. At this one, just multiply this whole with Z minus 3 and take the limit at Z tends to 3. Result is coming this way. But in this case, it is a pole of order 4. It means we must differentiate it. How many times? Yes. Suraj Kesari. Yes. Ujjwal Tripathi. Ujjwal Tripathi. Utkrish Singh.
Yes, sir.
Yes, Utkrish. How does
Yes, n minus 1
n
time,
minus
so
1?
3 times.
It means 3 times. So we need to differentiate it 3 times. And then 1 upon factorial 3. So it is mentioned here. You need to differentiate that one. This one, n minus 1 times, but this whole thing is to multiply with Z minus 1 to the power n also. Remember the formula. So we will multiply this by Z minus 1 to the power 4, so it will cancel out. We need to differentiate Z power 3 divided by this one 3 times. It's mentioned. You may differentiate, I'm not going to differentiate it. First time second derivatives, then again derivatives. But after taking the derivatives, we should take the limit at Z tends to 1. So result is coming this way. So I hope the point is clear how to find the residue of the function at a point. Now, if anyone have any question, any doubt, then you may ask. You may raise your hand. I'm giving 1 to 2 minutes. Sachin,
Yes, sir.
is it okay?
Yes, sir.
No one want to ask a question. I hope the concept is clear because no one raising a hand. Okay. So now our next topic is Cosi residue theorem. This is the very, very important theorems to find the value of any equation in complex analysis. Residue theorem. So if a function fz is analytic in a closed curve C, except at a finite number of poles within C, It is FZ is analytic. I hope you may see the pictures. We have been shown the picture somewhere. We may consider the same picture here. No issues. Suppose I've been shown here only 2 points. This one, this one. So FZ is analytic within this closed outer closed curve C, except finite number of points. These are here. Z1, Z2, Z3, Z4, so on. Then you all know that if there is a point at which function FZ is not analytic, then the procedure of the integration of integration may be changed. So initially, when we were having 1 point, then we use Cosi integral formula and some other things. But here, maybe the n terms, n points at this function is not there. Then the value of the integration FZ dz over C is equal to 2 pi I, sum of the residues of the poles within C. It is those points which are lying inside C, we may find the poles, we may find the residues at those points, and then we take the sum of them. And then multiply by 2 pi I will give us the value of the integration. Proof is very simple. I don't know if you have been revised all those things, then you can understand the meaning of the sentences. If FZ is analytic in a closed curve C, except some finite number of poles Z1, Z2, Z3, so on, Zn. You can see. So what we can do? We can construct a circle centered at Z1, Z2, Z3, Z4, so on, Zn respectively with small radii. So we are going to do like this one. Then the function fz will be analytic in an annulus region bounded by the circle C and the circle C1, C2, C3, so C4, so on, Cr. Non-intersecting factor. No circle is going to intersect with them. So if it is going to happen, then by extension of Cosi integral theorem, the value of integration fz dz will be the sum of the value of the integration fz dz over C1, the C2, the C3, the C. I hope you make this is clear because we have been discussing already. Extension of Cosi integral theorem. Now we need to find the value of this C1, C2, and C, and so on. So it's very easy. C1 will stop for this one, but we know the residue of fz at z equals z naught. Residue of fz at z equals z naught. Initially we have been defined it. You may remember it. Because B1 was the residue and the value of B1 was 1 upon 2 pi I integration C1 at z. So this is equal to residue of fz. So the value of this integration will be 2 pi I residue of fz at z equals z. Similarly, value of this integration is 2 pi I value of the 2 pi I into residue of fz at z equals z, and so on. We may use these results in equation 1. So what will happen? Integration fz dz over C is equal to 2 pi I residue of fz at z1 plus 2 pi I residue of fz at z2, and so on. So we may take the common 2 pi I residue of fz at z1, z2, z3, so on. So ultimately, these are the sum of the residues at the poles within C. So this is the Cosi integral theorem. Not Cosi residue theorem. Cosi residue. Now, we may see some problems based on the Cosi residue theorems and see how it is helpful for us to find the value of the integration. Evaluate the following integral using residue theorems. 1 plus z divided by z, 2 minus z. In the integration case, I hope you all remember, I've been explained some letters. What we should do? First, we need to draw the curves. So curve is C centered at origin and radius is 1. Then we need to find the points at which function fz is not active. So that point is 0 and 2. Then third was we need to check which point lie inside C. So z equal 2 is outside C. It is not going to affect anything. But z equal 0 is inside C. So z equal 0 is inside C. Then as per the Cosi residue theorem, the value of this integration is 2 pi I residue of this function fz at z equal 0. And residue of this one at z equal 0 is just simply multiply this whole thing with z and take the limit at z tends to 0. So z to z will cancel out, z tends to 0, it means numerator 1, numerator 2, 1 by 2 will be there. So 1 by 2 into 2 pi I, that is pi I will be the answer of this question. Why I, without solving I, yes please.
So we have a next class, sir.
Yes, I'm going to stop it. So,
Yes,
pi I is shown here that without doing anything, without any calculation, we give the answer of this question. If you keep the concept in your mind, then you can give the answer of the question immediately without using the theorems. So this is the beauty of Cosi residue theorems. Just we need to find the residue of this function at z equal 0, and we can find the value. Similarly, if anyone is going to change in place of here z minus 1, z minus 1, and here z minus 1, and circle is going to be z minus 2, z minus 1.5, minus z equal 1.5. So again, this z equal to 1 is going to lie inside this one, and then 2 will be outside this one. So at z equal to 1, you may find the residues. It means we need to multiply this whole with z minus 1. That will cancel out with this one, and z equal to 1. So z equal to 1, it means 1 plus 1 is 2, and denominator 1. So 2 and 2 pi is 4 pi. So within a minute, you can give the answer of a question by using the Cosi residue theorems. Okay. Now, wait a minute, I will take the attendance, then I will leave the class, please. So these portions now have been completed. Okay, now I may leave the class.
thank you, sir.
Thank you, sir.